So does anybody have any questions about what we went over last lecture? And so just to briefly review, we went over the concepts of branching and jumping. So as everybody was joking around before lecture about what while loops are. So you have an if statement where you are actually making some kind of comparison. I is less than j, I is greater than or equal to j. We went over the fundamentals of those. So a while loop is you're making some, or for loop, while loop, all of these types are, you're making some kind of comparison, and then if that comparison is met, you're executing the code. So what we're actually doing at the physical level in the advanced digital system is we're making the comparison in the opposite manner, so we determine whether or not we wish to actually go not do that code. Right? So we understand that there's PC plus 4 underlying the advanced digital system, and then we're actually going to branch the number of instructions that are required to execute that if statement. And we're going to go over a number of examples, and by the end of class today, we're going to actually have gone over a full while loop with an if statement inside of it. And then I'm going to show you some examples of how pointers physically work, both with referencing and passing by value and passing by reference. So we went over all these comparisons. And so one thing I want to point out from the MIPS screen sheet, that we have 32 registers in MIPS. And so at this level, when you're compiling from C to the assembly language, what you're actually going to be doing is you're actually going to be determining which registers you want to use. So in this specific case, so far we've been using saved temporaries. So S0 through S7, and we have T1 through T14, T through T15, which are the temporary registers. So we've worked a lot with those. But there are a number of other registers. So these A0 through A3 are variables that are passed to functions, and V0 and V1 are return functions. So you know how you have an int and a function, we'll just call it foo, and you're passing two integers, and let's say you're adding them together, right? So in the code, you would actually allocate A0 and A1 as your values you're passing to the function. You perform the code inside the function, and then you actually are going to jump register, so that JRRA, which we talked about last class, and then we're actually going to go back and we're going to turn that value with this V0 or V1 variable. And we're going to be going over examples of that today. But first I want to kind of describe what C programming actually is. So these two handsome gentlemen right here, this is Ken Thompson and Dennis Ritchie in 1970. These are the two people that invented C. And the reason they invented C, so basically before that there was the programming language B, which was the basic typeless programming language known as basic combined programming. And so the whole idea of typeless is that it was fully functioning on the machine level, meaning it was all zeros and ones. It didn't deal with integers, it didn't deal with strings, or all these things that you've worked with in coding classes in your C++ and your Java, right? So it was typeless because programmers dealt with computing devices low memory. So at that point, back in 1970, you had a huge computer that took up half of a room and it only held a megabyte. Okay? Nowadays, all your phones have, several gigabytes of memory. So you have, billions and billions times more just in the hand of your phone than they had total. So they were trying to get around these memory constraints. So what Ritchie and Thompson did in 70 was modify the typeless B programming language by adding data types for variables converting to the compiler to produce machine code. So you're able to write code in a data type. This is how recent it was. In 1970, they came up with the concept of an integer. They came up with the concept of a string or a bool. This is things that they were all doing there. And you're actually able to write the code. And so the other thing that they emphasized is that this specific type of code was meant to compile directly to the machine language through very efficiently in the machine code. So since C compiles directly to the machine code, the compiler may derive code that allows significantly higher throughput. So what they were trying to do is they were trying to write code that allowed them to understand how the advanced digital system actually worked. So the way we're going to be going over it in this course is you're going to be given some C code and you're going to be compiling it down to the machine language in a way that demonstrates that you understand how the code works. So this is where you understanding computer architecture versus computer organization really comes into play. Because when you write some C code, and we're going to be talking about this in a little down here, they have the ANSI standard, which we'll go over in a moment here. The general idea is that you want to be able to use efficient code that runs quickly on your machine, right? So in TGO 4.8, which is just this line, in 1983, the American National Standards Institute established an unambiguous and machine-independent definition of the C language known as ANSI-C. So if you've ever done C coding and you do the compiler and you GCC, and then you add the two flags, wall and ANSI, who in here has actually done that? Okay, so a couple of you, right? So this ANSI, what it means is you're adding a flag, which means your code has to meet the specific standard. And so what you're going to be doing in here is you're going to be learning about the difference between procedural and object-oriented code. So everything that you've done, most of you have coded in C++ or Java, right? And some of you might have some C experience, but it wasn't required for this class. Is that fair to say? So C++ and Java, and we're going to be going over the difference between object-oriented and procedural programming in a bit. But you use objects, right? So you're designing classes. You build this big object, and then you execute code based on the use of those objects, right? In C, since it's a procedural language, your code is actually going to be describing what the machine is actually doing, which is why I want to introduce it in this course. Because C++ builds on C, and then you're going to be later in this course learning about something called System C, which you can actually use to simulate and synthesize computer chips by basing on doing all this. Before you do that, I want to go over what C is. So to emphasize why knowing C is important, in 2005, 9 billion microprocessors were manufactured around the world, and 8.8 of them were primarily using C. Because you can actually do it to efficiently use the code. And so I didn't include David Griffith's position, but he works for Cadence Design Systems. But here, it's an important foundational language that requires you to understand the full stack of the technology. If you learn C, you'll understand computers at a much more profound level than if you don't. So understanding C will allow you to write more efficient code. And then when you take those principles that you use and apply them to C++ and Java, your code will run faster. Now, anytime, I've alluded to this before, you ever had an app that runs really, really slow on your phone and it's annoying as all get out? Oftentimes, it's because it's poorly written code. And so if you're a person that can write efficient code and someone downloads your app, for example, and they like your app, it runs fast, I barely notice it, then more than likely, they're going to buy something else for you, right? So learning these skills is something that will make you very valuable to any company, no matter where you go when you graduate. So the difference between object-oriented and procedural programming, we're going to formally define it here. Procedural programming uses a list of instructions to tell the computer what to do step by step. Whereas object-oriented programming is an approach to programming where all computations are carried out using objects. And then furthermore, I'm going to scroll up here so you all can see the behavioral, structural, and geometric modeling. So what you are going to be learning, you'll learn it in Verilog later in this course, and then you're going to be using VHDL in the 386 lab. Are these concepts of the difference between behavioral, structural, and geometric modeling. So if you're a computer scientist, you really only have to worry about the difference between procedural and object-oriented programming, because you're trying to design code based on what it is you're using. If you're using Java, it deals with the virtual machine, so you don't have to worry about pointers, you don't have to worry about memory management, you don't have to worry about efficiency that much, because the virtual machine takes care of a lot of that for you. But behavioral modeling, structural modeling, and geometric modeling are what you're actually doing to represent physical details of a machine. You can actually now use code to design computer chips, which seems like it makes a lot of sense, but that really wasn't the case until about 1980. When Alberto Sanguelli, who now is a professor at Cal Berkeley, but he was the founder of both Cadence and Synopsys, they came up with the idea of actually doing design automation. So what you're actually doing in 386 and later in this course is actually going to be doing these concepts. So behavioral modeling is an explicit definition of the mathematical relationship between input and output with no implementation information. So what that means is, like, let's say A equals B and C. So you can write Verilog code where I can represent a fundamental AND gate. So it's a physical representation. You all remember from 235 AND gates, OR gates, NAND, NOR, XOR, XNOR. So you can actually use this code, if you recall from section 3, you can actually write code to develop your own full adder. You can write code to develop your own arithmetic logic unit. You can write code to derive your own data path. You can write code to devise your own computer. And so there's different trade-offs. So behavioral modeling is a high-level one. You don't have to worry about how the computer works in terms of interacting with all the input and output with the I/O. You don't have to worry about the physical details, the underlying physical details, how it's actually synthesized, what type of silicon is it using, what type of, are you worrying about specific design cells? All things that you can learn in taking a digital VLSI course. So structural modeling is formally defined as the implicit definition of I/O relationships through a particular structure using interconnection of computers. So when you design, you can design some cells using some behavioral modeling, and you can say, all right, I want to design a full adder. Okay. Then you're going to use what's known as a wire to connect your carryout to another full adder, and then you have your output there. So you're using the cells there to design a full adder. Then you can use those cells and a bunch of AND gates, OR gates. If you recall from when we were going over what the type of multifunctional ALU is, you can actually use all those wires, connect them to multiplexers, bring in your select lines, which come from your opcode, and put that on the output. So by connecting all that way is known as structural modeling. So you've actually intuitively done all of this already. The new thing that you probably haven't dealt with is geometric modeling. And so when you're actually designing the physical details of a machine, you ever seen a picture of an actual chip layout and it has all these different colors and everything's running around and it looks all really neat? Well, if you go down to different levels, you have to design that using geometry. And so geometric modeling deals with how the system is laid out in the physical space. So let me zoom in a little bit on the Gaske-Kuhn chart. So all of this is traded off here in the behavioral, structural, and geometric space. And so everything that you're going to be learning throughout your academic career kind of really falls into one of these three areas, and they're all tied together at some level. Either it's behavioral, structural, or geometric. And you can see up here, you can see all the circles leading to all the different spaces. So at different levels, when you're designing behavioral systems, you're typically, when you're dealing with the structural level, you're actually just going to be dealing with the CPU or memory. And then you're dealing with the full level of chips. So each one of these circles here correlates to a different level of design abstractions. If you're doing something behavioral, algorithms, sign multiplication, restoring and non-restoring division. Everything that I was doing, you can actually do that in VHDL or Verilog, or you can do that in C, and you can synthesize it down. So how do you actually do all that in the structural level? So that's where you start getting into subsystems and buses. How do you connect all the pieces together? And then from there, you start clustering everything together at the physical level. So in order to actually implement those algorithms, you all have some familiarity with register transfer, right? So we understand how registers work. We tie them into cache memory. And from there, how do we actually execute that information? So the behavioral, we start with register transfers. And those, you take the registers, put them into the arithmetic logic unit. This RTL code is how it behaves. How you do it structurally is the arithmetic logic unit. And then down here, macros and floor plans. So I don't want to go into too much detail about what floor planning is, but the general idea is when you lay out a chip, it's a little outside the scope of the course, but when you lay out a chip, you know, it would be really weird if all of you were on one side of the room and I was just lecturing over here, right? That would be profoundly inefficient. You want to have everything spread out equally, and we do pressure and variation in temperature corners. So that way, you know, if I don't want to do it so that way Darren isn't doing all of his work, he's doing all the work for the rest of the class, so he's going to get burnt out, right? So that way, if sorry, Tori's using it, he's not doing anything back here. It's not efficient. We want to spread out the work, and that's known as floor planning. And then underlying the register logic. So you were learning about how the ALU works. Well, you actually do that using your adders, your AND gates, and your OR gates, right? So the logic's tying into there. And then gates and flip-flops, you're all familiar with that. And then what you're actually doing in the geometric level are cells. So if you actually design a cell, like the full adder was an example of a cell. I have two things going in. I have three inputs going in, A, B, and carry, and then I have a sum and carry out. So once you actually design it, you can just use the cell. Instead of having to rewrite it every time, you can just use a cell. It's very similar to a function in C++. Yeah.
So with the floor planning, would that correlate to how well the chip dissipates heat?
Yes. That's exactly why it's done. Yes. Any other questions? All right, and then finally, transfer functions, transistors, and polygons. So the whole idea there is with transistors, you'll actually learn how you have supply voltage and ground, and then you actually will have that should be P plus and N minus, the actual positive and negative. Then you have polygons, and then you have an input and an output. So this is a very simple description of how an inverter works. But then eventually I have to size it, and that's what the polygon is. So the transistor is the structural implementation of these transfer functions. How do you actually, and that's kind of like how do you actually transfer electrons back and forth throughout the computer system. So does anybody have any questions about this? I should probably also. Okay, so how do you write good C code? So are you all familiar with XKCD? So it's this comic. You guys, the more you learn about this, the more you'll appreciate it. So it's just start project. Do things right or do them fast. Write and fast. Code well. Are you done yet? No. No, and the requirements have changed. Throw it out and start all over. Does it work yet? Code fast. No. And then somewhere magically over here, there's just good code, right? So coding can be very difficult. I'm sure you're all aware of having worked long times and you think the code works and you run it, you run the compiler, and it just doesn't do what you asked it to do. And you've also all had that situation where you have no idea why the code works, but it ran. Yes, even Dr. Morrison said that several times. It can be very difficult. And so the reason why you want to understand how it's working physically is because this will actually allow you to understand how the code works better. And so this is an example of a function. So we have our included libraries, the standard IO and the standard library.h. And then this is a function where I am bringing in variables, and then I'm performing a while loop. Wise bear here. Sad face, right? So what we're doing is that while some value in an array vals is not equal to 0, we're going to do I is less than or equal to j, and then we're going to add the value of vals of I to the value that's in some pointer, and then we're going to increment vals of I, and then outside we're going to do I++. So that's just this is generic code, doesn't really execute much of anything other than to emphasize the points that I want you to learn in this course, which are memory management, array management, and how you actually derive this down into assembly and then machine code. So don't think of this as something terribly useful. It's kind of useless code other than how to do that. So I have this here, but in bold it says, this may look intimidating for those of you who have not dealt with this. However, it turns out you've learned everything you need to know to do this already. You've already learned it. You learned it in how you do your RTL language. You understand machine code. You understand pointers, because we've learned about load and store operations. You understand array operations. And I've taught you today about how those specific registers we use for return functions and array allocation. So recall base addressing. Base addressing is what we've been using at this point for load and store operations, specifically with arrays. So let me bring up the diagram again. Recall this. So the idea of base addressing, as you know, you take the 5-bit value from the register, you decode it into 32 bits. One of those values will be 1. You will select that specific register, and then from the immediate, you do the offset. And we've gone over this whole detail about how in an array, it's the base pointer. This value in the register tells me exactly where Jamar is, so Jamar is my base pointer here, right? And then my offset, if it's 4, we use base addressing, which means it's like the base addressing is beta addressing in the case of NIP. So you got 4 of them. So I'd have to add 4 to then get to Anthony. This would be my next element of the array. So we can also do this in the case of this sum value here. So what's going on here is int star vals is a pointer to an array, but int star sum is a pointer to an integer. Well, it turns out that we just do the same thing. It's an element, it's a value that's located in data memory, and instead of it being the first element of an array, it's just the first element of itself. Does that make sense? So what's physically going on when you deal with pointers is int star vals is a pointer to the first element in the array of its location in data memory. Int I is actually a value that's stored in a register A0, so it's in a local copy, but it's different than the value I that was passed. So if you're all the main function, right? They say. And so Lexus is the original value, and I want to do the copy function, right? So what I would have to do is I would do some sort of add value, right? So then I add Alexis, and then plus 0 gives me Shalia. So Shalia is my local copy that I'm using in the registers, but specifically for the function, right? So that's a copy. That means any addition that I do to Shalia's copy of the register doesn't update Alexis's, right? That's why. The reason I'm going over this is I know that the concepts of registers and pointers is a very common tripping point for students in code. You can get through the entire C++ class and still not quite understand what that means. So this is what's actually going on. So what I'm doing is if we're coming through here and then I have an array. So I started I0, whatever I is, so I pass I0 there. Jamar. And then what I want to do is I want to increment every time. So I say that value that Jamar has is not 0. And then I compare I and j, which I've passed through here. So I compare you guys. Are you less than or equal to him? If so, I just increment that value. And then I increment, and the next increment moves on to the next element of the array. Does that make sense? But if you guys, if he's greater than him, then we don't do that, and then we just increment. So that's going on over here, all independent of the main function's variables, right? So that's the important thing, how do pointers work. So here's how this is actually working. So these are this is from the, I should also say from the MIP screen sheet, these are all of the registers. That's actually there, and on the exam you'll have this available to you. So that register 0 that I alluded to last class is actually register 0. So the ones that you'll need to worry about in this course are those. You're not going to really need to worry about global stack and frame pointers. You'll address those in other classes. But the whole idea is that arguments, these are the arguments to a function. The function results, v0 and v1. I want to have a result from a function. Saved temporary and saved registers and temporary registers you're already familiar with. Oh, you'll have the whole MIP screen sheet. I will have a copy available to you. So I provided a copy for you on Blackboard of the MIP screen sheet. It's under content, and if you look there when you're preparing for your exam, you'll be able to have all that information for you. So it will be available for you on the test. All right, so what I want to do, so basically everything I just said, your stuff I've already told you. So we want to start with, what is this actually? How do we actually compile this from C to physical details? So in this specific case, we need to know the difference between pass by value and pass by reference. So A0 through A3, we're using this in the function, right? So we know that vals is an array, right? So we are passing the value that's in the function A0 is going to be pointing to the physical location of the first element of the array of vals, right? A1 is going to contain the numeric value of I. So something's happening in the main function. I then copy the value to a different register, and then all the operations go on there. A2 contains a pointer to the address and data memory where sum is. So what you would have to do is, let's say K was returning the value of sum, right? So what I would have to do in order to have it operate on is that I would allocate a specific place in data memory. I would perform a load operation, stored operation, where I would then take it and put this physical detail in memory. There's a forest here. So now the value that's actually being passed is a pointer to the actual location where forest is. Does that make sense? It's not pointing to K at all. The thing is that when it updates, we actually have to make sure we update that. So the difference is, when I'm updating I, any changes I make to I stay in the function. Do not change. Any changes that I make to sum have to be changed back in the main copy, right? So that's something, the pointer is actually maintaining the physical communication here. It's two different copies, but you have to maintain that update. So when that gets updated, you have to automatically do that. Does that make sense? And then A3 contains the numeric value of J. So this is an example of the actual difference between pass by value and pass by reference. So we formally define pass by value as a copy of the value of the actual parameter that is stored. And pass by reference is a copy of the address of the actual parameter that is stored. So here, this example is pass by reference. Pass by value is you're 5, right? Okay. You're 5 now. But any updates that happen here don't affect that. Pass by reference means, okay, you're 8. Okay, you're in the location of where 8 is made. So any update I want to make to sum, I say, hey, I'm updating sum. And then you go, hey, you're now 6, right? That's how pointers work. So that's the difference between pass by value and pass by reference physically. And so now we're getting to this while loop. So how do while loops actually work? So while is just the same thing as an if statement, except at the end you're going to have a jump back to that specific value. So if you recall from last lecture, we did if I is less than j, I is greater than or equal to j. We discussed all those different comparisons. Well, it turns out we're just doing the same thing. The first thing we're going to do is just do the comparison. So while vals I is equal to 0, what I want to do is I want to get that value from the location. So from last lecture, what's the first thing that I have to do? I know it says it right underneath, but what's the first thing that I have to do there? If I have vowels of I in some sort of comparison, like a if statement or a while loop here, what do I need first before I can do anything else? I'm sorry, what? I heard it. Yeah, well, I multiply 1 by 4. Yes, there we go. So teamwork saves the day, right? We want to multiply I by 4 because when we're actually running it, we don't know what the value of I is, right? If this was vowels of 5, the compiler would actually have an intermediate value of 20 already in there because it's compiler-driven encoding in the micro engine. However, because of the fact that it's not, we actually have to do multiply by 4. And so the way we do that is we shift left by 2. So here what we're doing is A1 contains the value of I. We shift left by 2, and we store it in T0 in a temporary register. Next, because of that, what we need to do is that's the offset. So if we figured out that I is equal to 5, and we multiply by 4 because of the byte addressing, then it's 20, right? But that's just 20 off of that initial address. So, Jamar, you're my person I picked today to be the base player. But so Jamar is the value of A of 0. I've now multiplied A of 1 by 4, so I know how many bytes I need to get to the value I need to get to next, right? So I need to add the value that I just calculated by multiplying by 4 to the value that Jamar has. So I add those together there. And in this case, I've used an efficient reuse of temporary registers, but if you put T1 on the exam, it's fine. So I add that, and now I've gotten the actual physical location of the place I need to go. So now my offset's 0 because I'm pointing to the exact location. So I load word, I load it into a temporary register. By doing this function, I then get the physical value of vowels of I that's now contained in that temporary register. And because I want to execute the code when it's equal, what that means I want to branch if it's not equal. So I compare 0 and T0, and then I have this sign extend value. So that's straight from the MIP screen sheet. And so when you're actually doing this on an exam, the way that I always do it is when I did it, I would just draw a little line and leave it blank, because you have to afterwards. That's how you have to calculate how many values you need to go by, right? So then the next thing is I is less than or equal to j. So if I is less than or equal to j, I want to do that, right? So that means I want to jump if I is greater than j. So what we need to do is, if they're equal, I'm going to branch, right off the bat. I'm sorry, I only want to branch that way. So here, if it's, we can set less than if j is less than I. So in that case, it was A1 and A3. So j, we set if j is less than I, and we can, I'm sorry, we put that value in. I'll do it right this time. So I is greater than j. That means we want to figure out if I is less than j, right? So we set less than, and we're going to put it in T0, and then if j is less than I. Does that make sense? If j is less than I, we're going to set that value, put a 1, and then we branch not equal T0, 0, and then the number of instructions. Does everybody understand how I did that? I'm happy to go over it again if you didn't. And so here, this 4.13 here, in C you must use this star sum function for variables that is passed by reference in order to indicate that you must load the variable from data and store it to the data memory after every loop. So that's what I was talking about here. So what happens is, by adding sum, that star in front of it is known as a dereference, and we'll go over that in a little bit. So I dereference it. There's an actual physical copy of the temporary value. And then what I do is I actually perform a store operation where I store it in the memory. And then at the end of the function, the first thing I do is I do a load operation here. So there's a local temporary register that keeps the value, and then I update it in data memory. And then when the function's over, I pass it back. And so this is an example here of an actual base addressing. So you have your instruction, right? And then what happens is you take the value from RS, that's the base pointer. You add the offset, and the value of the pointer is that specific location. And then the value is going to be stored back in that register. Y'all see how that works? Hey, while you are writing it, feel free to ask lots of questions. I understand that pointers are complicated, that C conversion is complicated, and now I'm throwing all these physical details of the machine at you. Right? The objective here is to, the way I've structured this specific section is to make it understandable, because I feel that pointers are too often glossed over, or they're taught improperly, or they include all these pass by value and pass by reference without ever explaining to you what it is that you're actually is actually going on. So I understand it can be intimidating, and I understand that it can be difficult. My goal is I want you to understand it. So please, if you have any questions, do not feel intimidated. No one's going to think you're stupid, because believe me, it takes everybody a long time to get it. So I just want you to make sure you know that. All right, and so this is another example here where instead we're just pointing to sum. So that previous one I had was val 0, and there's a number here. So this is the base pointer there, and then that's an A0, and then we store the value in T0. The offset here is an integer. In this one, the sign extended value is going to be 0 because we're pointing specifically to sum. Does that make sense? There's a specific location in data memory. But otherwise, it's the same. And then for store word, we add this value, we get the offset here, and then we store it in data memory. And likewise with sum, it's the same thing where we take the value of the register, add it to 0, and we store it there. So this becomes important because at the end of the function, we have to make sure that the local copy of the temporary register updates to you. So in the function, I'm going to allocate some temporary register that says, you're sum for now. When we're done with the function, we're going to do a store operation that says, all right, we're going to store you in data memory. This is what the function did to sum. And then when you restart the function, the next thing we do, we're going to do a load operation where you're going to load it back into the copy of the register that we were using for the function before. And so that's what all these drawings represent. All right, so this here describes how you actually represent the code with pointers and ampersands. So the pointers are referenced to in C code using the following two characteristics. So the ampersand contains the address of the variable. So if I say int ampersand j, this is pointing to the physical that's the value of the physical location in memory, not the value of j itself. Does that make sense? So ampersand j is I'm pointing forth. If I dereference it using a pointer and I say point star of j, what that actually is 5, the value 5. And we'll go over an example where I've compiled some C code for you, and I show you how the physical detail actually works. And so I actually in that specific one, I actually generated a segment. You all familiar with segmentation faults? How many of you coded in C? How many of you ever done a segmentation fault? How many of you want to scream at your computer and throw it out the window? Yes. I actually generated code that did a segmentation fault, and you're going to see what a segmentation fault actually is and why you're getting that. So hopefully, next time you're coding in C, that never happens again. And so the star is the contents of the address of a dereference, which is what I was talking about before. So star J would be 5, ampersand J would be the location, or the value pointed to by. So that's known as the indirect operator. And so here, star sum plus equal vals of I, the indirect operator means that in the function, I have allocated a temporary register that's going to have all the values. So I do a load operation where from memory, I get the value, I put it in the temporary register, and that's my indirect operator, because that's what I'm going to indirectly operate on. I perform all the operations on the temporary register, and then the last thing I do in the function before I jump return is I perform a store operation and put it back into data memory. And so example 4.6 is going to be an example of this. So 4.6 is going to be very similar to the type that you will see on your exam. Yes?
Maybe I missed this, I just don't remember, but temporary and so temporary is T, what is A?
A is the values that you're using to pass to the function. So we'll go over this in a second, but A, vals I, int, sum, and J. Those are the address variables. So specifically meaning that these will, yeah, does that make sense?
So A is like the address.
Mm-hmm.
Okay.
Yeah, specifically want to use them when you're passing them the function. Okay. Does that answer your question? Awesome. Any other questions about it? So in this specific question, I want you to translate the following code, C code, to MIPS assembly. Vals is an array of words, so array of 32 bits, allocated in memory where I is A1, the pointer to sum is in A2, J is A3, and the base address of the array of vals is in A0. So when I did this, the first thing I would do is I would just be like, base of vals A1 is equal to I, A2 is equal to the pointer, and A3 is equal to J. Or you can just do A0, A1, A2, and A3. Whatever helps you understand better and keep track of everything. So the address of the first instruction of the while loop is 256. Using the return the value using V0. And then the return address is in RA. So I've told you all of the inputs to the function. I've told you VO, that's how I want you to return it. And then the single most common error made by every student, no matter how many times I jump up in here, just to make sure you're the group that doesn't do it, the single most common error is people forget to do JRRA at the end of the function. So in the solution down here, this line here, that is the forgetting that is the single most common error that students make on any of my exams. And if you think about it, you have to jump back to where you were before the function, so it's required. But we'll go over this step by step. Right, so this is the problem we've been working on by going through here. Right? So first, all of these instructions numbers actually are the values, right? So 256 is where we're starting because that's what the problem indicated. So first thing we have to do is we have to multiply I by 4. And actually, I'm going to zoom out just a little bit so you have both the function and the solution on here. So first thing we need to do is we need to get the value of I. As you guys said earlier, we have to multiply I by 4. The simplest way to do that is shift left logical. So if I is 4, we end up at it, we just shift left by 2 and become 6. Yep. I'm sorry, 4. It has to become 16. Second, we're going to add the value of I times 4 to the base address of the array. So the base address of the array is in register A0, as indicated by the problem. And then we add T0, which we got from the previous instruction in 56. And then load word here. We're going to load that value that we got. Here I have indicated T1. We're going to load that value from the data memory into a temporary register. Right? So we now, T2 here now contains the value vals of I. And then, so the first thing we're going to do is we're going to do while vals of I does not equal 0. So we want to branch past this if it's equal, right? We want to do the opposite. So we're going to do branch if equal. T2 is the current value of vals of I, and register 0 contains the value of 0. And I've left this blank for now. So I want to show you the trick that I use to calculate the numbers. So when you're doing the problem, you get to this first branch, leave it alone. Okay. So the next thing we need to do is I is less than or equal to j. So first thing we do, we're going to do set less than. And so we're using that register T3 that's going to contain the value if j is less than I. So I see I have S2 and S1. Why did I do that? It should be A2 and A1. Yeah, good thing I'll be right the rest of the way. So A2 and A1. So j is in A2 because that's the value we pass to in the function. And then A1 is in I. So if j is less than I, then I'm going to set the value of T2, which is a temporary register, equal to 1. And if you look at the MIPS green sheet, remember the topical guide objective we discussed last class about what set less than is? So then I want to compare that and then say, here T3 is equal to 1 if j is less than I, T0 if j is not less than I. And then the next instruction, branch equivalent, T3, 0, and once again I've left this blank. And the reason why is because that's where all of my jumps are going to go to, right? So first, I would branch past this. If I branch past that, I'm not going to do either of these two instructions, correct? I'll eventually go down here to where I'm going to want to eventually get to this jump value, because then jump comes here. But if it's while means I want to go all the way to return, right? So I would actually jump to that one, because nothing got changed. I'm sorry, to 269, because you want to do this one last thing. All right, but what we're just going to focus on here. So now we are inside the if. Okay, so before I move on further, does anybody have any questions? All right. So what I want to do here is the sum value is stored in data memory. So I need to perform a load operation to get that value. Now, because the offset is 0, because I know the exact location, I don't need to do any shift left logicals here. Does that make sense? So here I've added in a load word of A of 2. Now A of 2 is the physical location in memory of sum. So by using a star here, what I've done is I've dereferenced it, which means what I want to do physically is I want to load the value from data memory and put it in a copy of a temporary register, which is going to serve as our indirect operator. And so that's what's going on here. So I've loaded T4 is now equal to sum. And so what I'm doing here is, next thing I want to do is I want to take the value of vals and add it. So I'm going to take, remember we stored T0. So the base pointer, sorry, the value of T0 is in, I'm sorry, the value of vowels of I is in T0, right? So we have, I'm sorry, in T2. So we've loaded it there. So T2 plus T4, I'm sorry, we add here T4 plus T2 there. So T4 is sum and T2 is vowels. Because sum plus equal is actually, so in this case, T4 is the current location of sum. And then this is actually star sum equals star sum plus vowels of I. Now in this case, we know that vowels of I is located in T of 2. We know that sum is in T of 4, and we want it stored in this register T of 4. So that's why instruction 263 is that way. And then because I've updated T4, which is our sum, the next thing we need to do is we need to do a store word instruction. So the indirect operator and pointers, that's what 263 and 264 are. 262, I go to the location where the pointer is, I put in an indirect operator, I perform the operation because I need to take the values from when I'm doing the addition using registers, and then this store word in 264, I'm actually storing it back there. So perform the operation, and then I get it back. So we are now past our if statement. So this is where, here, so we store word, and then vowels, oh yeah, so we have one more, vowels I plus equals j, right? So vowels I plus equals j, we have the value of T0, which are T2, so then we're going to add a, which is j, which is A3, right? So this 265 is here. So we add the value to T2. But since I've updated a copy of the array, I now have to update it in data memory. So that's what this store word operation in 266 is. So what 266 is doing here is I'm taking the value from T2, which is the current value of vowels of I, and here T1 is the location in data memory of vowels of I, right? So that's why I always add these, because it allows you to save you some temporary registers and time. So I go, okay, I need to take the value of vowels of I, and I need to store it in the location of vowels of I, right? So the physical, the temp indirect operator is stored in T2, and I do a store word. I know the exact location, so my offset is 0, and I store it in T1. And so now that value is updated. So every time I change something that has a pointer, physically I have to update it. So that's what is physically going on in a pointer. So now when I want to go past the if statement, the I++ is the next instruction, right? So before we actually do add of I, which is this one, right? I need to get to 267, right? .261 to 267 is where I need to branch to. So that's where I'm going to fill in my first empty spot. So what do we know physically about the MIPS data path with regards to instruction count? It comes out of the PC, and then we do what every time? I heard over there, PC plus 4. Why do we do PC plus 4? Interesting, right? Because we have to do 4 bytes in order to get to the next instruction. So automatically, the physical detail of the instruction is going to be such that it would just normally do that for you. And so but I need to get here. So this is now 1, 2, 3, 4. I need to add 5 more instructions, right? So 262 plus 5 becomes 267. So the value that's stored, remember when we talked about branch instructions last class, what's the value stored in there? Is it the number of instructions or is it the number of instructions times 4? Compiler-driven encoding in the micro-region. I want to reduce area times 4, right? Because if I don't do times 4, what ends up happening is I have to have some kind of shift value as a little bit of area. So 261, the way you do it is you take the final instruction you want to be at, which is this case I'll just do final minus initial minus 1 times 4 every time. So in this case, it's 267 minus 261 because that's where our first branch is, right? So that's now 6 minus 1, which is 5, times 4, which is equal to 20. So this value that's put here is going to be equal to 20. That makes sense so far? All right, so when we do this I++, what we're actually doing here is add of I. Add I, A1 plus 1. So you're updating the copy of the register, but you're not actually updating anything in the main function. Does that make sense? And so this jump to 256 here, which is what I've added next, is when you've completed the while loop, I want to physically go back to the instruction number, which is why knowing what 256 is important. If you say jump 256, it will go to that exact value and we'll start all over. So jump 256 here in instruction 268 physically goes there. So the pseudo-direct addressing, what's actually going there, the value of 256 is stored in a 26-bit value in the instruction because we also require the 6-bit opcode. So then we multiply by 4. So that's actually 256 times 4. And then we concatenate the 4 most significant bits from the program counter. And that gives us our 32-bit value. And so in this case, this was 20. So now this branch equivalent, I actually want to get here to this next instruction. So using that same equation, who can tell me what the value should be? What should the value be if I want to get to 269 from 259, what should that value be? What was the equation that I just set up? You're saying it right, say it a little louder.
Minus 1 times 4.
Correct. So what's the final one? Because everybody say it together. What's the final one? What's the initial one? What's 269 minus 259?
10.
What's 10 minus 1?
9.
What's 9 times 4? Very good. So what's physically going on in this branch instruction is I want to move 36 bytes. Physically, the computer organization increments at 1 already. So what you're actually doing is you're moving 40. So here I want to move 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry, 9. So that's what's physically going on in the advanced digital system. And so what I'm doing here is I know here that return I plus equals vals. So that return value is V0. I know that I is A1 and vals ends at T0, right? I'm sorry, T2. So T2 is the value of vals of I. So what I'm doing here, A1 plus T1 is going to be returned. And so that's the value that's going to be there. So then it's actually stored in a local copy of the register. So what the actual end of a function is with that return value, is you're actually putting a copy of the result in the local register. And then the last thing you're going to do is you're going to jump to the next instruction that you're going to execute in main. So that's what this jump register means. So you actually have a 32-bit value that's contained here, and you're going to return to that value. This could be any, that's the value that's stored by the compiler at the beginning. So what we're doing here is we are designing a specific function. So to review, I'll go over this again. Vals of I does not equal, so this initially is a while loop. Vals of I does not equal 0. So it's physically going on here. I need to get the value of I and multiply it by 4 because the computer organization indicates we use byte addressing, right? So we multiply it by 4 using that first instruction, shift left logical, and we store the location, so the value of I times 4 in T0. And so A1 was actually the location of I. A0 is the initial value of the, is the value of the base pointer of val. So if I add T0, what I'm doing is I'm adding my initial location. So you think of it as addresses if it's like your friend lives at 8210, right? So you start at 8,000 and you have to add 210 to get to that specific place. In this case, we're adding T0, which is I times 4. Now we know the exact location of vals of I. And then we load the value of vals of I into a temporary register, which is an indirect operator. So as you're probably noticing, the concept of arrays and the concept of pointers, physically it's the same thing. The difference is the number. So the specific value of the pointer to sum is just one of them, whereas vals of I is some number of values in the array. So next, I want to, if vals is not equal 0, so I want to branch if it's equal to 0. So in that case, just BQ, T2, the value of vals of I, register 0 contains the actual value of 0, and we leave this blank, even though we've calculated that to be 36. Next thing I want to do, I want to branch. So I want to perform the operation if I is less than or equal to j. So if I is greater than j, I do not want to perform the operation. And I want to branch past those instructions. So I set less than if I, we said that j is less than the I because that's the value we calculated. If j is less than the I, then T3 is equal to 1. If T0 is going to be equal to 0, if j is not less than I, which means it's less than or equal to in that case. And then branch equivalent, T3 is 0 because we want the value to be if it's actually a 0. And then we leave that blank as well. Next, we're going to deal with store sum. So it's going to be star sum equals star sum plus vals of I. So we already have the value of vals of I, right? So we have to perform a load operation where we're getting the value from data memory. We know the exact location because that's what's passed to us in this function. This value here is the exact location of sum, not the value of sum itself. So to perform a load operation, we store it in a temporary register, which we've called the indirect operator in the previous topical guide objective. Then T4 plus T2, T2 is the location of vals of I, and then we store it in T of 4. Anytime we update the value of T of 4, the indirect operator, we perform the store word operation to update the local copy in data memory. From there, afterwards, we're incrementing the value of vals of I, so we increment the local indirect operator T of 2 by performing T2 plus A of 3, because A of 3 is equal to J. And since we've now updated another indirect operator, we perform yet another store word operation. So in that case, we store the value in T2, which is our local copy of vals of I, into the actual location where vals of I is done. From there, we calculate 267 minus 261 minus 1 because this is where we wanted to branch to because we're branched to the I++. So here, 267 minus 261 is 6 minus 1 because of the PC plus 4 in the data path, which we'll cover in section 5. And then times 4, so that gives us the value of 20. So here I would say 267 minus 261 minus 1 times 4. And then we include a jump instruction here because afterwards this bracket means I want to jump back there. So jump to 256, that's the initial instruction. So in the event that we actually go through everything, we want to go through here. So the only way we wouldn't do the while loop is if physically, when we do this branch here at 259, we have to break the whiles not equal j, which means I want to go to the instruction past that jump. Does that make sense? So 269 minus 259 is 10, minus 1 is 9. We multiply that value by 4, we get 36. So in that case, we get 4, 8, 12, 16, 20, 24, 28, 32, 36. And we're there. So then here, doing the return, we're going to put the value of I plus equals vals of I. So we're taking that value of T1 that we know in A1, and we're storing them in V. And then last but certainly not least, what's the last thing I want you to do on this problem? Jump return. Why am I emphasizing it so much? Yep, most common mistake students make. Because they get so focused on doing these other things like, oh, I just want to be done with this problem, I hate this problem, I want my life to be over, they forget. But that's why I'm putting it in there. I want you to just remember. And then that value actually physically takes us back to main. Does anybody have any questions about this? Yes?
Why did we start at 256 again?
256 was what the compiler designated this specific code to be. In the problem, I've indicated that the address of the first instruction of the while loop is 256. So you have some number of instructions that indicate main, and then what the compiler will do, and if you want to learn more about this than you've ever wanted to, you can take a compiler design course, but it will allocate the functions after that. But in this specific case, what I said is the block 250, the location in memory 256 correlates to that specific location. Any other? Yes? Mm-hmm. Yes. Yeah, the reason I left them blank is because I found over time teaching this course that if I just throw the number up there, then what students will do is what you always do, you take the notes and write down the number and you don't learn why. So I deliberately left it out so that way we could work together to calculate the number. Yes?
When we do the load word, why is it 0 parentheses right?
Okay, so the offset for is when we calculate arrays. Specifically for star sum, it's just 4 blocks. Oh, I'm sorry, 4 bytes, right? So it's just one element. So when I'm pointing to if I'm giving the location, I don't need to do any offsets. So when it's 0, what's actually physically going on in the data path is the arithmetic logic unit receives the location of sum and the value 0. Any other questions? Okay. Yeah, pay a lot of attention, particularly in the video when you're going over the assignment. Pay attention to the notes that I have there, because that'll help you out quite a bit when you're working through those as well. So example 4.7, I've included this here as an example to show you what's going on with the star and the ampersand and how these pointers are actually working. So here I have just a standard IO function, or it's an int main void. And so I've allocated 2 integers, x and y. I'm going to zoom in a little bit here so you can see more. And I have 2 star integers, right? So I have two references. So here, what I've done is I've put the value of negative 100 in x, and I put the value of 200 in y. And I have said that the value p of 1 contains the location of x, and p of 2 contains the location of y. Does that make sense why that's going on here? So then there's a bunch of fprint statements. I want you to see what's actually going on here. And this is where I've generated the segmentation fault. And hopefully after this, you'll have actually understood what the segmentation fault actually is. So the first printf is I'm just printing out the values. So it's going to come out as negative 100 and 200 here. Next, I have printed out just P1 and P2. I didn't add a star or an ampersand. So if I'm saying print out the value that's stored in P of 1, what that means is the registers that contain P and 1 contain the actual location in memory, right? So the function allocates a certain amount. And so that's to answer your question that you just asked, Matthew. Yeah, I was just brain-farting your name here. But Matthew, the question you just asked, there's a specific amount of memory that's allocated to a function. And so there's a specific base that's allocated based on what the operating system wants. So you're actually permitted to have negative numbers because it's compared to a specific value of 0. It's not always pointing to the top of the stack. It moves around. So in this specific place, these are the two locations. And as you can see, the difference between these is 12 and 16. So there's a difference of 4. So the specific machine was actually using byte addressing. And then by dereferencing the values here, I actually say, what is that physically contained in those registers in the data memory? In the data memory as opposed to registers. And that's why we get negative 100 and 200. So for those of you who've coded in C, the number of times you've worked on this and you get weird large numbers, that's because you're actually asking the program where it physically is in memory. And so what I've done next is I have changed star P100 to 300. So basically I've dereferenced P of 1 and then I've said 300, which means what is the actual value? So here P1 is equal to P2. So what this is that updated X, and now I have two pointers, but now I've told them to point at the same location. So in this case, now they're now pointing to the location of Y. So the location of Y is P of 2, and now it's pointing to P of 1. And so when I do this fprintf again, I want the values of X and Y first, and it's actually been updated to 300 because I've dereferenced the pointer, and I said, hey, this thing. I said I dereferenced it. I had a local indirect operation. I said, hey, I'm updating to 300, and you went, hey, 300. So that H value has 300. So that's why 300 and 200 is there. And now I've actually changed the location of the pointers. So I said to the other pointer, I said, hey, let's both point at the same location, which is why we do P1 is equal to P2 here, which is why in that second one here, both of them point to the value of 200. And last but certainly not least, I added P is equal to negative 100. So what I've done there is that the program, the compiler-driven encoding of the microengine, and I'll go over this and then I'll dismiss you, allocated this specific amount of memory. And it's like, 603 billion, right? And then I just say, all right, this pointer is actually pointing to negative 100. So it's way over here, right? So the first thing I do is say, tell me the values of X and Y. Again, it's 300. And then the second I say, what are the locations that P1 and P2 are pointing to? And that's negative 100 and 603, like I've updated. But since P1 is now pointing to a location that's either not in memory or hasn't been allocated by the program, you think about, we had this direct associativity and set associativity. Well, there's no more associativity. So when I say, give me the value, I want to dereference it, what's the value? It's like, that's not associated with anything. Segmentation fault. And so that's why segmentation fault poured them. The segmentation fault, you've asked me to do something that I cannot physically do. Program over. I'm dumping you. Right? That's what that means. Does that make sense to everybody? That's what's physically going on with pointers. All right. On that note, we'll start with 4.8 next week. I'll post. I'm not next week on Thursday, and then I'll see y'all then.